Okay. Okay, so good morning, everyone. Dr. Nat here. You are in ECC 3129 and ECC 3119 class. Hopefully everyone is here. We have 49 people, 10 people are missing. Okay. So this is the outcome for week 2 and week 3, what we will learn. So we have learned about the amplitude modulation fundamental. We learned about the equation. We learned that there is VM, that is the instantaneous voltage of the modulating signal. We also talked about VC, the instantaneous voltage of the carrier signal, and the product of these two gives us a modulated signal, which is the AM or the amplitude modulation. So that is for the standard AM modulation, or actually it's just standard amplitude modulation or standard AM. And then we also talked about coefficient of modulation, modulation of index, and also modulation percentage. We discovered that if the modulation or M is greater than 1, then you would have overmodulation, which will cause distortion in your signal. Okay, so a participant said the speaking language in English. Not sure what that means. Okay. Okay, let me repeat myself. So we talked about coefficient of modulation, modulation of index, and also modulation percentage. And as I mentioned to you before, if the M is greater than 1, then you will have overmodulation because the typical range for modulation is from 0 to 1 or less than 1. And if you have more than 1, that would cause distortion in your signal. And this is not what we want. And then we will talk about AM voltage today, power, and also current distributions and time domain analysis. If we manage, we will go over some circuit for AM generation. Otherwise, I will focus this on our recorded class in the coming session. Okay. So this is what we saw earlier. This was our modulating signal. And this is our carrier. The carrier is inside. Before the modulated signal is applied to the carrier has a constant amplitude. And then this is a AM modulator circuit, a general representation of that. I accidentally switched it off. Got it. Share content. Okay, am I clear? Everyone can hear me?
Yeah.
Sounds okay? All right, great. Okay, so I'm going to continue. Hopefully, I don't make any technical mistakes. Okay, so this is the generic device representing AM modulator. You have the modulating signal, VM. You have the carrier signal, VC, and this is overall multiplied in a nonlinear device or a circuit that we will learn later on. And the outcome of this is an AM modulated waveform. Okay, so just a little recap here. Nothing fancy. So this was the equation that we saw earlier, right? This was the instantaneous voltage carrier. Of course, we can convert this to power. We can convert this to current. And this is the modulating signal. The difference is here in the subscript, you have a C, you have an M here, you have an FC, you have an FM here. So 2 pi F is equal to omega. Sometimes in other textbooks, you would see the equation being represented by omega instead of 2 pi F. So just something to take note of. Don't get confused. It's basically the same thing. Okay. And then we talked about the AM envelope, whereby the VM has to be less than VC. If VM is the voltage of the modulating signal. If VM is too big, the modulation will be too much, and it will cut the carrier, and you would get something that looks like, I think we have it. Oh, you would get something that looks like this. Overmodulation, whereby the waveform is flattened at the 0 line. Okay, so back to this. So when the amplitude of the modulating signal is greater than the amplitude of the carrier, distortion will occur and you won't get the waveform. You will get a waveform, but it will be hard to demodulate and get the original information, which means that your information will be distorted. Okay, moving on. And then we talked about the equation that makes up the VM, or the instantaneous voltage for amplitude modulation. And it consists of the VC and also VM. Sorry, this was not it. Let me erase this. This is VM. So VM is basically composed of VC sine 2 pi FCT plus VM sine 2 pi FMT times with sine 2 pi FCT. To generate such a signal, you need to multiply the modulating waveform. Okay, so your free meeting will end in 10 minutes. Let me upgrade. I think I unsubscribed this. Give me a minute, 5 minutes. Make this. So lecturers are kind of like teachers in a way that we have to pay for our tools. For teachers, they pay for their chalks. We pay for the Zoom, we pay for the Padlet, for our own markers. So hopefully that can change in the future, but now it doesn't look like it. But Ultra Blast is very helpful and we don't pay for that. So that's great. And give me 5 minutes. I just need to upgrade my plan so that we can record this continuously. Upgrade account. Okay, please order. Okay, so it is done. So let's continue. Okay, so back to this equation. Why am I going over this equation again? There's a reason for this. We will see this again when we are discussing the circuit. Okay, so for the VAM, what you see here is you need to have an addition of the carrier signal, VC sine 2 pi FC. I shouldn't write over it, okay? And then it needs to be added to a product of the VM sine 2 pi FMT, which is the modulating signal, times with the carrier signal without the VC. So how do we achieve this? We need to design a circuit that will do this for us later on. Okay. So next one. So this is just the same thing as before. Oops. Any questions so far? Everyone's okay? How's everyone doing? Don't sleep. I know you're at home, but don't sleep on me. Okay. Okay, so we also talked about the modulation index and also the modulation percentage. Recall that VM needs to be less than VC. And we have this equation. Okay, if VM is going to be less than VC, then the equation is going to be VM is going to be the denominator. The VM is going to be the, what do you call the top one? The top guy, and VC is going to be the denominator. Always, you need to remember I can't talk today. You need to remember the order of the VM and VC. Okay. And then from this equation, you will also get VC times M is equal to VM. How do you remember this equation? Remember that VC is always going to be bigger than VM, right? VC is always going to be bigger than VM. And modulation is always going to be from 0 to 1. So if VM needs to be smaller than VC, therefore, the equation should be M times VC equals to VM and not MVM equals to VC. So this is wrong because MVM will obviously give you a smaller VM than VC. But VM is actually a portion of VC. Okay, if that makes sense. So just trying to make things relatable to you. Okay, next. Okay. And then we have our over-modulation and distortion. We talked about this as well. We saw clipping of negative peaks. So it looks like this. You still get a waveform, but you can't demodulate it. What is demodulating? You will figure this out later in AM transmission and receiving. And then we have equations that help us look at the oscilloscope and we can tell what the M is from these equations. So you have the Vmax and the Vmin, and then you can find out what is Vm, you can find out what is Vc, and you can also find out what is M based on what you see on the oscilloscope. And again, to remind you, the Vmax and the Vmin is not from peak to peak. Okay, it's not peak to peak. It is from the 0 to the, it's just one side, okay? Only this guy. It's not peak to peak. So don't make that mistake when you are plugging in the numbers later. Okay, next. So we talked about this example. We did it in class. And then we talked about sidebands and frequency domain. Whenever we have an AM process or AM modulation, the product of the modulating signal and also the carrier frequency or the carrier signal will produce sidebands. And this sideband is upper sideband and lower sideband. So upper sideband is FC plus FM, the frequency of the carrier plus the frequency of your modulating signal. So if this is FC, then you would get something over here, FC plus FM. So this is your sideband, upper sideband, FUSB. And then another one would be over here, which is FC minus FM. And this would be your FLSB, okay, lower sideband. And then based on the trigonometric identity, we talked about this as well. When we substitute this identity into our VAM equation, we will see that the expansion gives us the exact part where our sideband forms. Our sideband is FC minus FM over here. This is the lower sideband. And this is our upper sideband. Okay. And you can also see that the amplitude for the voltage is Vm over 2, whereas this guy is Vc. Okay, if we were to change this in the terms of Vc, we can use this equation. Okay, probably my mini iPad is too small to do this. Okay, MVC Vm. So we can use this equation, substitute it here to find out everything in VC if we want. But we will do this later. Just recap for now. Okay, any questions up to this point? Any confusion you want to ask? Want to clear up? Is everyone okay? Okay, all right. So if you have any questions at any point in class, just unmute yourself and ask, okay? Because I cannot see your face. I don't know what's going on behind the camera. So just unmute. All right, so continuing, we talked about the frequency domain display. We cannot see the sidebands when we are observing it in time domain. Therefore, it is best if we represent the AM in terms of frequency so that we can know exactly where our sidebands are, or to make our calculations easier. So here is another equation I want you guys to focus on, which is the bandwidth called B, whereby bandwidth is FUSB minus FLSB. And remember, this is FM plus FC, and FLSB is FM minus FC. Oops. So basically you would get, oh, sorry, this is wrong. Okay. So FC plus FM minus FC minus FM. Is this correct? Okay, so you would get, I need to put this here. You would get FC will be cancelled out, and FM minus FM would give you 2 FM. Okay? Oh, my handwriting is pretty bad. Okay, so I hope you understand where we get this, and this is a this is a pictorial representation of why it is 2 FM. Okay, right? And then this was our last slide, last lecture on Monday. We have our carrier frequency. Okay, this is our carrier frequency. And then the amplitude of this guy is represented in the frequency domain by how tall this guy is. And the frequency is plotted based on the frequency. So you can't really tell the frequency in the time domain, but if you know the number, you can immediately plot it in the frequency domain. And then we have the modulating signal over here, the modulating or the intelligence signal that is used to modulate the carrier. And when we modulate the carrier, we will get sidebands. This is our USB and this is our LSB. And we plot it according to its amplitude. The amplitude is going to be smaller than the carrier frequency. And then we have our frequency FC plus FM, which is on the right. And we have our frequency FC minus FM, which is on the left. Okay. So this is the representation in time domain. So you can't really tell there is sidebands, but there is over here. But yeah, it's not obvious. So just stick to frequency. Time domain is something that you would see in the oscilloscope if you want to. And sometimes it's helpful, but not in this case. Okay, moving on. Any questions about this diagram? Everyone's okay? Everyone understands this diagram?
Yes.
Okay. Okay, thank you. Right. Okay, so this is a new slide. We haven't talked about this one yet. So sidebands from complex modulating signal. So whenever the modulating signal is more complex than a single sine wave tone, multiple upper and lower sidebands are produced by the AM process. What does this mean? This sentence is telling us if our modulating signal is not just a sine, but a combination of sines, so you have many waveforms inside the modulating signal, you would get more than the USB and LSB. You will get a lot of sidebands, not just like the pair that we saw earlier, right? So for example, a voice signal consists of many sine wave components of different frequencies mixed together. So here, this is the indicator that this is a complicated or a complex modulating signal. Now recall that voice frequencies occur in 300 to 3000 hertz range. You don't have to memorize this. I'm just telling you. So if the carrier frequency is 2.8 megahertz, then the maximum and minimum sideband frequencies are. This is a question. It's telling you that the modulating VM is between 300 to 3000 hertz, which means that instead of one frequency, you have between 300 to 3000, and within this band is your modulating signal. So it's very complex. It's within this band. You can't really pinpoint what frequency because it's a bunch. It's a combination of many. Okay, and this is in frequency. So this is your VM. Our FC, this is FM. Our FC is 2.8 megahertz or 2800 kilohertz. So now we are asking what is going to be the maximum and minimum sideband frequencies. Okay, so if we were to recall what we have learned so far about carrier and also sidebands, we know that this is going to be our FC, and this is going to be our FUSB, and this is FLSB. So if our if our modulating signal is going to be a range, therefore our sideband is also going to be a range. Okay, so this is FC plus FM. This is FC minus FM. So your minimum FM, okay, this is, how do I do this? FM minimum is 300. So you would find the minimum first, and then you would find the maximum sideband after that. Okay, so how do we do this? So 2,800 plus 3, we already convert this into kilohertz. Okay, kilohertz. So this is the maximum. Okay, this is max FM. This is FC. So FC plus max FM will give us maximum range for upper sideband, which is over here. Okay, 2803 kilohertz. And for our lowest sideband, this is our max FM. And this is our FC. So FC minus maximum FM will give us the lowest, how do I say this? The greatest number for lower sideband. Greatest number. Wait, no, that's not the right sentence. It will give you the most minimum, if that's the word. Okay, 2,800 minus 3, you would get 2,797, and you would get it over here. And then for the minimum one, the minimum is, let's try to find it as well. It's not done here, I don't think so. So 2,800, this is FUSB minimum, 2,800 plus, we need to convert 300 into kilohertz. So that's going to be 0.3. 1, 2, 3. Yeah, 0.3. So that's going to be 2,800.3. So that is why they're not doing it, because it's very, very small. And then you have the other one, FLSB, for this side over here, which is going to be 200 minus 2,800 minus 0.83. Okay, very, very small. The gap should be like smaller than this, but you know, the picture is to help you understand things. So that is why it looks like that. So the range is between 2,000, for this guy at least, it's 2,800.3 to 2,803. So this is the range for the upper sideband. And for the lower sideband, it's going to be, this is 2,799.7, I think. And this is 2,797. So the range is between this 2,797 to 2,799.7, if my math is correct. This is the lower sideband range. I need to improve on my handwriting. Online class. Okay, so the next question is, there's no bandwidth question here. Okay, so if we were to calculate the bandwidth, we would use the maximum. Maximum, not the minimum. So this is something to take note of. When you have a range, you want to find out what is the bandwidth, please use the maximum frequency of your modulating signal. So in this case, your maximum frequency is 3,000 or 3 kilohertz, and bandwidth is 2 times FM, right? So 2 times 3 kilohertz is 6 kilohertz. Okay, so any questions about this question? Everyone okay? Does anyone need to me to repeat this? Okay, no questions, right? Okay, next one. Whenever the modulating signal is more, okay, we already did this one. I duplicated this. Okay. Okay, next one, sidebands from complex modulating signal. An example, I'm going to give everyone 10 minutes to do this. I'm going to call someone randomly to help me out. Okay, so 10 minutes from now, 11:40, let's solve this. Pretty easy. We already done the example previously. So this is quite similar. Okay, 10 minutes, 11:40, I will call someone. In the meantime, if you have any questions, you can ask me. Excuse me. Okay, 2 minutes left for your break slash exercise. So hopefully everyone got this. It's easy. Should have been done in like 2 minutes. And I finally bought a new calculator. Okay, 1 minute to go. I hope everyone is back. Okay, time's up. Okay, I want to ask Aslam. Is Aslam there?
Yes.
Okay, Aslam, what is the carrier frequency in this example?
980 kilohertz.
980 kilohertz. Okay, thank you, Aslam. Hilman, are you there?
Yes.
So what is the minimum modulating frequency?
975 hertz. kilohertz. Sorry. 900.
900. The
975. Minimum 975 kilohertz.
Okay. So minimum is lower sideband.
975.
Okay, but my question was, what is the minimum modulating frequency?
Oh, modulating. I thought it was the minimum sideband. Sorry.
So what is it?
The minimum modulating frequency. Is it the 5 kilohertz?
10 kilohertz. No, actually it's not given, but it
Not
tells
given.
us, yeah. So that was a trick question, by the way.
It's-
Okay, thank you, Hilman.
Sorry.
So here they tell us the transmit modulating frequencies up to 5 kilohertz, which means that it's telling us the maximum, but it's not telling us the minimum. So we don't really know, but we can assume it's 0 maybe, but it's not given, so we don't work with that number. Okay, so what is the minimum, what is the maximum upper sideband? Can I have Irie to answer that? Maximum upper sideband.
USB, I think is 985 kilohertz.
985 kilohertz. Does everyone agree with this?
Yes.
Doctor.
Oh, backup kawan eh. Okay. Thank you, Irie. Okay, so what is the bandwidth here? Can I get, okay, a girl pula eh. Nadia Fitriana, what is the bandwidth here? Is Nadia there? Okay, Nadia is not there. Oh, ada. Okay. Okay, Nadia, what is the bandwidth?
Ten.
Complete answer with units.
985 minus 975.
985 minus 975. No, what is the answer with units? Betul dah tu, dah betul dah. 10
10
unit.
kilohertz.
10 hertz. Is this correct?
Kilohertz.
Kilohertz, okay. Okay, so basically it's just 2 FM max, right? If you have max, the maximum modulating frequency, you can find out the bandwidth. Okay, thank you, Nadia. So that is it for the example. Hopefully everyone got their break, got their toilet break, and understood the example that we just did just now. So next one is the frequency spectrum of an AM broadcasting. So your radio, they don't broadcast, the radios that we listen to is not in AM. We listen to FM broadcasting, but we do have AM broadcasting, which is typically used by the military or by amateur people who play with radio transmissions and stuff like that. So AM, it exists, but we don't really use it, but it's there. So for AM broadcasting, they are actually spaced every 10 kilohertz across the spectrum from 540 to 1600 kilohertz. So this is just an FYI, you don't have to memorize this. So here you can have one radio station if you want to have your own radio station. This is the second one, third one, etc., etc. So they are spaced 10 kilohertz across the spectrum. Okay. So now we move on to our next topic, which is called digital AM modulation. So when complex signals modulate a carrier, a broad spectrum of sidebands are produced. We know this already. We've talked about it. According to the Fourier theory, complex signals such as pulses, rectangular waves, square waves, triangular waves, sawtooth waves, or distorted sine waves are made up of fundamental sine wave and numerous harmonic signals at different amplitudes. So what they're trying to say is, even though they look really complex, but they basically or essentially is made up of a sine wave plus harmonic signals. Harmonic is the multiplication of the sine itself. So harmonic, have we talked about harmonics? I believe we have. So it's going to be 2 FM, 3 FM, 4 FM. So this is the frequency of the signal inside that is a combination of the modulating signal, if that makes sense. So you have your first signal called FM. It's added with 2 FM, added with 3 FM, added with 4 FM. So when you have all of this together, you have a really complex waveform looking, but actually it's just composed of these things when you break it down, okay? So you don't have to memorize this. This is just an introduction. So these are types of complex signals, and we will talk more on this. Assume that a carrier is amplitude modulated by a square wave that is made up of a fundamental sine wave and all odd harmonics. Only odd harmonics here. So you have a fundamental over here. This is your square wave fundamental sine wave frequency. And then you have, it is a summation of the fundamental with the third harmonic, which means that this is going to be 3 of whatever fx this is. And then this is going to be f5x. This is going to be 7fx. Cancel, cancel. Okay. Okay, so I feel like you are going to be confused with this fundamental versus the carrier. But remember, this is the modulating signal. This is the modulating signal, VM, and this is our carrier. The VM is composed of many stuff because it's complex. So the fundamental sine wave is the fundamental sine wave frequency, and it is also added up with the third harmonic, fifth harmonic, seventh harmonic. And this typically happens because the circuit is very nonlinear, or the circuit has some, it's not really good at what it's doing, so it creates these distortions. So this is why a signal modulating signal becomes complex, okay? And of course, you have this as well. So this is not the sideband yet. Hey, wait. So that is carrier and all that will produce sideband everywhere. This is not the sidebands. It is, wait. Sidebands produced by the fundamental and its harmonic. Oh, this is already the sideband. So they're not showing the FM. Come on, FM. Okay, sorry, scratch that. I mistook this for the modulating signal. This is actually the sideband already. So they already modulated the carrier, and this is the sidebands produced by the square wave. Okay, so I do not have the FM or the modulating signal, so I do not know how this was obtained. Okay, so let's just take it at its value, okay? So moving on, our first digital AM modulation called the amplitude shift keying, or ASK. So this is our modulating signal. It looks like a rectangular wave or a square wave. The figure shows AM wave resulting when a square wave modulates a sine wave carrier. So this is our modulating signal, and this is what happens when the carrier is modulated. Now, there are two instances here that we need to take note of. This is A and this is B. So A, the M, or the modulating percentage, is 50%, which means that it's modulating only half. Only half, because it's 50%. What is M? Remember, M is at VM over VC. So it's only going half of VC. And then we have percentage of modulation is 100. This is when you go completely, when we go for 100% modulation, it eliminates the carrier entirely. So you will be left with a straight line. Okay, so amplitude modulation by square or rectangular binary pulses is referred to ASK. ASK is used in some types of data communication when binary information is to be transmitted. So if you have a modulating signal or you have an information that consists of 10111000. This is when you use a modulating signal that looks like this. So this is your 1 and this is your 0. And then for the M, it depends on your circuit, how far you want to make it. Is it going to be 50? Is it going to be 30, 70, or 100%? Okay, so this is called ASK, amplitude shift keying. Okay, moving on to the next one. We are going to talk about on-off keying or OOK. Okay, OOK. So this is a crude type of amplitude modulation. Crude meaning to say it's not well, crude means, how do I say this? It's not precise. It depends on you. You have to do it yourself, okay? So basically you have to like press on, off to actually modulate your carrier. So this is achieved by turning the carrier on and off, and we are only transmitting the carrier. There's no modulating signal. The modulation is you. You are modulating. You are the modulating signal. When I turn on, off, I am modulating the carrier. Therefore, I am the modulating signal, as weird as that sounds. So this is why it's called crude amplitude modulation, because you do it yourself. For example, the first one, digital AM modulation of OOK, is done by the Morse code by using dots and dashes. Now, I really like this. A dot is a short burst of carrier and a dash is a longer burst of carrier. So this is your dot, right? And this is your dash. So what does it mean when you have these dot and dash? So the figure shows transmission of the letter P, which is dot, dash, dash, dot. Dot, dash, dash, dot. Dot, dash, dash, dot. Okay, so this is representing the letter P. So, okay, so there's a pronunciation of did, da, da, did. Don't know how you actually say that. Sidebands are still generated by on-off signals, even though we only are transmitting carrier. The sidebands are resulted from the frequency or repetition rate themselves plus harmonics. Okay. So the first one was ASK, amplitude shift keying. Second one is OOK, on-off keying. So there is a common word here, keying. K is for keying, on-off keying, amplitude shift keying. Okay, any questions so far? Everyone okay? All right, I'm just going to continue. If you have any questions, please unmute yourself. So we are going to talk about effect of over-modulation and modulating signal distortion. So for A, this is a sine wave of 500 Hertz modulating a 1 megahertz carrier. So this is our carrier. And then we have a modulating signal of 500 Hertz. Therefore, we would get this as our upper sideband and this as our lower sideband. So therefore, the bandwidth for this guy is going to be 2 FM, which is 2 times 500, which is 1 kilohertz. And then for B, this is when our 500 Hertz sine wave or modulating signal is distorted. When the modulating signal is distorted, we will get sidebands in the second, the third, the fourth. This is the original LSB, but you will get harmonics of the LSB. Similarly, this is the fundamental USB, and you will get harmonics of the USB. This is because your modulating signal is not clean enough or your circuit is bad, poorly made. Okay, so you would get harmonics. So assuming amplitudes beyond the fourth harmonic are insignificant, usually that is less than 1% of the VC, then the total bandwidth of the resulting signal is about 4 kilohertz instead of 1 kilohertz. That would result without over-modulation and distortion. Okay, so what does this sentence mean? Without distortion in my modulating signal, I would get a bandwidth of 1 kilohertz. But when I have a distorted modulating signal, my total bandwidth of operation is now 4 times greater due to the harmonics. Now, instead of just focusing here as my bandwidth, I have to take note that this is also generated at bandwidth beyond without the distortion, right? So now the bandwidth becomes bigger, and we don't like this because when we have a bigger bandwidth, we will get more noise, and it's not efficient. You are overusing the spectrum, etc., etc. Okay, and it's going to be higher in cost because you are using more spectrum, and also takes up power. There's a lot of things to it. Okay, we will talk more about that, but hopefully everyone understands that when we have a modulating signal, the modulating signal can be clean. It's a single sine wave, or it can be distorted. And if it is distorted, it will produce harmonics, and it will impact your bandwidth, and it will become bigger. Okay. Okay. Let's try to finish AM power. And then we will take a 10-minute break again. I know online class is very tiring on your brain. So let's try to go for a few more slides, and then we will take a break, okay? Okay, so let's talk about amplitude modulation power. So the total transmitted power denoted as PT is simply the sum of the carrier power, PC, and the power in the two sidebands, PUSB and PLSB. Wait, I'm recording, right? Okay, I'm recording. Okay, so this is your equation, PC plus PUSB plus PLSB. We have seen this equation before when we expanded using the trigonometric identity, and we found this guy, right? Remember? So for power calculations, RMS values must be used for the voltages. RMS values must be used for the voltages. So how do we get RMS values? Root mean square value. You divide the V by square root of 2. Or if you don't want to use that, you can multiply by 0.707. I know square root of 2 is not exactly 0.707, but it's close. Okay, we are approximating things when we are engineers, so it's okay. So here is the VAM in RMS. So I am now dividing all my V's, all my voltages with square root of 2. Okay, I'm dividing it with square root of 2 because this is VRMS. Okay, so that gives me, and then if I want to convert this to power, so power is V squared over R. I would square this and divide it by R. I would square this, divide it by R, square this, divided by R. Same case over here, square this and divide it by R. And I would get something that looks like this. Okay, this is the equation. Okay, I would get VC squared over square root of 2. R over R plus VM over 2 square root 2 over R, and then VM over 2 square root of 2 over R. Okay, so when we have square root and also square, we can get rid of things, obviously. So this is going to get rid of itself, and you will bring down the 2. Okay, you will get rid of this. This becomes 4. 4 times 2 is going to be 8. And then same case over here. 2 to the power of 2 is 4. Getting rid of the square root. So 4 times with 2, I will have 8. So now my equation becomes this guy. VC squared over 2R plus VM squared over 8R plus VM squared over 8R. Now, where did my sign go? Where did my sign go? It's still there, but we are assuming the sign is equal to 1 here. And typically in power, we don't deal with instantaneous power, which means that we don't follow this. We just want the RMS, which is something like this, the average. RMS is almost like average, but it's not really average. But it is used to approximate the average of a alternating amplitude or something that looks like a sine wave. Okay, I don't want to find out what the T is at every instances. So I'm finding the RMS. How do I find the power? I use VRMS squared over R. If that makes sense. If you don't understand this, you can ask. Okay? Okay. So this is our equation. So this is RMS. We got this from our RMS voltage to get our so-called average. Okay? And remember that we talked about M equals to VM over VC, or VM is equal to MVC. Remember, VM is a portion of VC, so it's always M times VC. So you can substitute that, you can substitute that over here to replace VM so that we have our equation all in VC. So what you would get is, after factoring things, do I have to do this? I can, but it will take some time. Let's not do it. But if you want the derivation, you can come see me, or you can request in class if you want, I can do it. But otherwise, we will go to the shortcut version, which is, we will get this as VC squared over 2R. And this is going to be 1 plus M squared over 4 plus M squared over 4. So I can add these two together. I will get 2M squared over 4. Okay, 2M squared over 4. So this would give me 1 over 2. So this is where the 1 plus M squared over 2 comes from. And VC squared over 2R is just PC. Wait. Okay, yes. Because this is RMS, okay? The 2 comes from the square root of 2. And we already squared that and it becomes 2, okay? So for anyone interested to know how we got this equation, I can't leave this. I have to do it. Okay, so for anyone interested, let's just factor out VC squared over 2R first, and we will get 1. Factoring out VC squared and factoring out 2. So I will get 4R over here, and I would get M squared over here. And then I would get the same case over here, M squared over 4. Oh, I already factored out R. So I would only get that. Okay, so I took out this guy, took out VC squared over 2R from this guy, took out VC squared over 2R from that guy. So I am left with 1 plus M squared over 4 plus M squared over 4. And then I add these two together. I get the 2M squared over 4, which gives me 1 over 2. So it becomes 1 plus M squared plus 2 times PC. As for this guy, why is it called PC? Why is it converted into PC? Because this is V squared over R. But remember, you have to do this in RMS. So this is not the actual equation. The actual equation is VC over square root squared over R. So your VC is VC squared. Your square root of 2 becomes 2. You bring this down. So it becomes VC squared over 2R. So that is where you get your PC. Okay. So in the exam, if I give an equation, if I give it, sometimes I don't, you will use an equation and derive other equations from that equation if necessary. So knowing P equals to V squared over R, knowing what RMS is, knowing P is I squared R is important. Okay, so you will have to like flip the equation based on these equations. Or times 0.707, okay? Okay, so this is very messy. Hopefully you have your own notes because this is very ugly. Okay, after this example, we will take a break. So let's do this example first. So this is our equation for the power transmitted for the AM. So this is PC times 1 plus M squared over 2, right? So for example, if the carrier of an AM transmitter is 1000, and it is modulated by 100%. So your M is equal to 1. And your PC is 1000 watt. Find the total AM power. So that is easy. You just plug it in. So 1000 is your PC. 1 plus 1 squared over 2. So this is basically 0.5. So this is 1.5 times with 1000. You will get 1500 watt. Okay, so let's take our break. Let's come back at 12:16. Okay. If you have any questions, you can ask them now. Otherwise, please take your break. Oh, forgot. Oh, forgot. I forgot. We need to do this example, 10 minutes. So you will take your break plus do this exercise. Okay lah, I will be generous and give you 12 minutes, extra 2. So, what happened? No. Okay, come back 12:18 p.m. Do this. It's easy. It's going to take you like 2 minutes. And so this is going to this. Okay, so we have 3 minutes. Hopefully everyone has done this example. 3 minutes for your break / exercise time. 2 minutes. Okay, 1 more minute. If you're sleeping, wake up. If you haven't done the exercise, do it. Okay, time's up. Okay, so can I get Afiq to tell me the total power? Is Afiq there?
Hello, hello.
Ada. Okay. So total power, how did you calculate that?
I take the 85% modulation and turn it into 0.85 and then plug
Okay.
it in into the formula. The
What?
1 plus m to the power of 2 divided by 2 times PC. And then yeah, I'll get 40.8375 watt.
8375. What?
40
40.
40 point
Sekejap, berapa? 40
uh,
point?
84.
Oh, 84 watt.
Yeah.
Betul, okay. So you use M equals to 0.85. Your carrier is, sorry, this is carrier. Your carrier is 30. So
Yeah.
30 plus 0.85 squared divided by 2. Is that it?
Yeah,
Is that
plus 1. Yeah.
okay? Okay, thank you, Afiq. So my next question is going to be for Emilia. What is the power in one sideband? Tak dengar? Can't hear you.
Hello.
Hello?
I
Yeah,
got 5.42 watts.
your power in one sideband is 5.42 watt. Okay, so how did you get this? Can you tell us?
PT, the formula is PT minus PC over 2.
Over 2. Okay. So PT minus PC would give you PLSB plus PUSB, right?
Yes.
Okay. So, okay. Thank you, Emilia. So what Emilia did was, so we know that the equation for PT is PC plus PUSB. plus PLSB. Okay, so PUSB and PLSB has the same power, which means that you can make these two together and you can write this as PC plus 2 PSB. This is just like generalizing the sideband to become SB, and you have two of this. So PT. You know what PT is because Afiq already found out the power for us, and we know what PC is. So PT minus PC divided by 2 will give you the power for 1 PSB or 1 sideband. Okay, so the answer is 5.42. I don't know. I didn't use my calculator. Let me double check it. So 0.85 squared divided by 2 plus 1 times with 30, okay, 40.84 watts. So minus 30 divided by 2, 5.42. Okay, so that is correct. Any questions about this question? Everyone understood what happened? Any questions?
Yes.
Yes,
Understood.
understood. Okay. Yes, other question. Okay, so moving on to the next slide. Thank you for answering. The next one is relating AM in terms of current. Just now we converted voltage to become power, and we know that if we want to convert voltage into power, we need to use the voltage in its RMS form. Okay, which is dividing it by square root of 2 or timing it with 0.707. Now, what is it for current, right? So in the real world, the AM power is determined by measuring the output voltage and calculating the power with P equals to V squared over R or P equals to I squared over R. As I mentioned to you before, you have an equation, you flip it over using these basic equations. Now, we already know this equation. Now, how do we find out the total power transmitted in terms of current? Same case over here. We have IT squared times R. And if I rearrange this to make the IT as our subject, this becomes PT over R and the square root of this entire thing. So eventually, this gives us IT equals to IC square root of 1 plus M squared over 2. So how do we get this? So we know that we have, this is our PT. Wait. I forgot how to derive this. Do I have it here? No. Okay, so it's lunchtime and my brain is not working. Let me get back to this when I have an idea. Right now, I'm blank. So this was from our initial, oh, sorry. It's just PT, by the way. It's just PT. So we are substituting our square root of PC 1 plus PT is equal to PC plus 1 plus M squared over 2 divided by R. So PC over R will give me I squared C. And then I have this guy still, right? Okay, I still have the square root. So I get rid of the square root. So now I only have IC square root of 1 plus M squared over 2. Okay, so that is how you get this equation. Okay, almost there. We're almost there. Next one is finding the power in each sideband. This should have come first. Finding the power in each sideband. So we already talked about this, and we know that if we expand this equation, right, we are just multiplying PC with the bracket. So we would get PC plus PCM squared over 2. Okay, so now if I bring PC over here, I get PT minus PC equals to PCM squared over 2. And we know that PT minus PC is basically 2 PSB. Remember our example just now? PT minus PC is 2 PSB. So this is equivalent to this guy. Therefore, 1 PSB is equal to PC m squared over 4. Okay, so the equation that I have in red box is very important. You will use this. You will see this a lot. So this is the first one. PSB is PC m squared over 4. And this one, IT equals to IC square root of 1 plus m squared over 2. And then we have the PT one. The PTP equals to PC 1 plus m squared over 2. I did not box this one. I boxed it here. Okay, and this is your general equation to make you understand. PT is generally equal to PC plus PUSB equals to PLSB. Okay, so these are marked in red for a reason. Okay, so when we are talking about the power in each sideband, we are going back to the slide we discussed just now. So PC power is basically just PC. It's not going to be changed at all. But the modulating, the sideband produced by the carrier with the modulating frequency is going to be m squared over 4 times with the PC. So it will always be smaller than the power of the carrier. And we know this for a fact because sidebands is always going to be smaller than the carrier. If it's bigger than the carrier, then there's something wrong with your waveform. Okay? So the lower the modulation percentage, okay, this sentence, the lower the power in the sidebands. So if you look at this equation, if your modulation percentage is the maximum, which is 1, you would get PC over 4. But if your M is less than 1, let's say it's 0.5, so 0.5 squared would give you 0.25. So you have to multiply this by 0.25, which is going to be divided by 4 compared to if the modulation was 1. So the lower your M, the lower the power in the sidebands. Okay. So the carrier power is unaffected by the modulation and remains unchanged. Only the sidebands is affected. Okay. So AM power example, an antenna has an impedance of, oh shoot, I don't have it, of an unmodulated AM signal, produces a current of 4.8 amperes. The modulation is 90%. Calculate the carrier power. Okay, so it's missing. Let me find out what the value is. Give me a minute. This one is AM power. AM power, example, okay, 40 ohms, 4.8 ampere. Okay, this is okay. So that is the value. The antenna has an impedance of 40 ohms dot. An unmodulated AM signal produces a current of 4.8. Okay, so this is unmodulated AM signal. So what does that tell you? 4.8 amperes. The modulation is 90%. So calculate the carrier power, the total power, and also the sideband power. So this is actually a simple level question. For your exam, you can expect a more complex question where you have D, E, F for one question. So it's going to be a lot of parameters. And from the scenario, you will have to find out all these things. So in my class, I will try to do simple questions first, but I will give you assignments that are more complex so that you have an idea of how the test will be like, if that's how you would like it to be. Of course, I want you to understand what is going on in class. So assignment will be the best way to do that, okay? Okay, so let's do this one. I have the answer. Oh, I don't have the answer. So let's find out what the equation is for these guys. So an antenna has an impedance of 40 ohm. We know that this is the carrier current. This is unmodulated. So this is going to be our IC. The modulation is 90%, so that's going to be 0.9. So what is the carrier power? So carrier power is PC. Total power is PT, and sideband power is PSB. Okay. So how do we approach this problem? Anyone? Anyone wants to try? So let's go back to our slides. So we have IC, we have M. Sorry, we have M, we have IC. We want to find PC, right? Okay. What equation will help us find that? Would it be this guy? We have IC here, IT here, and we have M here. We can find the total current. From the total current, we can find the PT, I guess. So let's bring this equation over. IT equals to IC. So let's just park this first. Oops. IT equals to IC square root of 1 plus M squared over 2. Is that right? Okay. So that is the first equation. I believe we can find PT using this. And then from PT, we have this guy. PT equals to PC. I can find out what is PC because I have these values. I have this value from this guy, assuming. So let's park that equation here. PT is equal to PC 1 plus M squared over 2. Okay, what else? If we know what the PT is, we know what the PC is, we can know what is the PSB. Okay. So I'm going to let you guys do this on your own. I will upload the slides with the answer for you to cross-check. I want you guys to try this yourself, okay? So next. Okay, so we are going to move to the next topic, which is called single sideband modulation. Now, single sideband modulation is not supposed to be covered in this week, but I feel like it is more appropriate to introduce it today rather than later, because we will talk about circuits, and then I want to like lump sum all the circuits to generate this modulation together later on. So I want to introduce everything first, and then the circuit, lump sum everything together. Okay, so don't worry about it. Let's just learn. It's not of your concern anyways. I'm just telling you that the order of the topics is a bit different than the course info. That's all. Okay. So single sideband modulation in AM, 2/3 of the transmitted power is in the carrier typically, which carries no information. We know this. Okay, we have this. We have the sideband, and the carrier is always higher than the sidebands, and it will take up the most power compared to the sidebands. So no real information is contained, the real information is contained in the sideband. The carrier does not contain information unless it is modulated. But basically you are wasting power just to make the carrier exist. So to improve the efficiency of AM is by suppressing the carrier and eliminating one sideband. Now, if you eliminate this and eliminate that, let me make this nicer. Okay, so you know that you have a lot of power consumed by the carrier. And then I obviously do not like this. So we want to get rid of this. And we also want to get rid of this or this. What you're left with is only one sideband. Now, why can I get rid of one sideband and leave the other? And why do I not have to retain both sidebands? Because they contain the same information, only that their frequencies are different. Okay, so they are supposed to be identical. Supposed to be lah. Okay, so if I can retain only one, I am actually cutting down a lot of power, which makes my system more efficient. So the first step to do this is actually to suppress the carrier and then suppress the sideband. So to suppress the carrier, this is called double sideband suppress carrier, double sideband suppress carrier, or double sideband only. We will just call this DSB for short. Okay. After this is if we suppress the carrier, DSB, we are still left with double sideband. We suppress this guy, but our sideband is still there. So we have two. That is why it's called double sideband. So I still have two when I suppress the carrier. But if I suppress the carrier and one sideband, I am only left with one. So this would give me a single sideband. So you will have DSB, double sideband, in which it means the carrier is suppressed, but the sidebands are still there. And the other one is you suppress the carrier plus one sideband, so you are left with one sideband only, and this is called SSB. So let's take a look at what DSB is first. So this is a time domain display of a DSB AM signal. Note that compared to a standard AM modulation that we have seen before, our AM, oh, this is ugly. Our AM modulation, it looks like this, right? And we have some like this. You have this part. How do I undo this? Okay, click here. Okay, so this was how our waveform looked like for a standard AM. But if you eliminate the carrier, you would get like pinch waveforms. It's not completely flat, but it's pinched. And this pinched is a change in the phase. A change in the phase. Okay. How do I explain phase? So phase is in layman terms, is how I understand this is when you transmit a signal, it has a certain time. Okay, let me draw this. I don't want to confuse you. Okay, so let's say I am transmitting this wave. I want to transmit an identical wave with the same phase. Okay, so I have to follow the timing of which this wave starts. So this gives me two identical phases. Now, if I do not want these two waves to have similar phases, I can start my wave, my second wave, this is the first one. The second wave will start later or it starts earlier. So let's try to say that it will start later. So I need to follow the same shape. So it will look like this. Now they are not aligned. They are not aligned because they have different phases. Okay. So I hope everyone understands this simple explanation of phase. Similarly, I can start it earlier than the first wave, and this would also give me a different phase. The only way I can achieve similar phase is by starting two waves happen at the same time. They need to happen at the same time so that their phases match. Now, it does not apply to identical waves only. Okay, so this is a little bit physics, but it will help your understanding later. Okay, so it doesn't apply to just identical waves. It also applies to other types of waves. For example, you start the waves together, but this is a different wave, but they have the same phase. Because why? They start together at the same time. When they are aligned, you would get constructive interference that will give you peaks as the output, the end. Okay, so that is phase. Now, here, when we go back to our time domain display of a DSB AM signal, note here it says, oops, here it says note the phase transition. What does that mean? So first you go in, oh my God. First you start like this, right? Like this. So naturally you would follow this pattern. You would follow this pattern, but here it's not following the pattern, it's flipping it. So you would get like a mirror of this guy, which is actually, you are not following the aturan masa. How do I say this? You are not following how the wave should behave like. You are switching things. When you switch something, you are changing the phase. Okay, so this is what it means. When they say note the phase transition, the phase is changed. So this is a very unique characteristic of the DSB waveform. When you see a change in the phase at this pinched part, you know that this is a suppressed carrier and this is a DSB. Very, very unique to the DSB. So you have to understand what it means for the characteristic of a DSB to identify it, okay? Any questions about this one? Okay, everyone okay? So, or just sleeping? I don't know. Hopefully everyone understood this part. If you have any questions, please unmute yourself. Otherwise, I'm just going to continue a bit. Let's try to continue until 12:50. So another 8 minutes. Bear with me. Just a few more slides. Okay, another 4. Is that okay? Hopefully in 8 minutes we can finish this. So double sideband suppressed carrier, we already talked about this, or DSB. A unique characteristic of DSB is the phase transitions that occur at low amplitude portions of the wave. We talked about this in length just now. In the figure, note that there are two adjacent positive going half cycles at null points in the wave. So this indicates a true DSB signal. So DSB are generated by a balanced modulated circuit. We will lump up all the circuits together in week 4, I believe. And then the DSB AM saves significant power, but it is difficult to demodulate at the receiver because the carrier is missing. When you don't have the carrier, this is going to cause problems when you want to retrieve back the information because you don't know how the sidebands were formed. It was the same case where I looked at the frequency diagram and I don't know how the sidebands were formed. So that is the same confusion. When you demodulate your sidebands, you want to know what is the FC, so you will get the FM, right? So if you don't have the FC, you don't know how to demodulate it. So sometimes DSB is not preferred because of the difficulty to demodulate. Okay, so this is the time domain that we discussed just now, and this is the frequency domain. It's just a similar standard AM, except that we do not have the carrier. The carrier is suppressed. This is indicated by the dashed line. Okay, moving on. So the benefits of single sideband signals, before we dive into what DSB is. Oh, sorry, this is not DSB. This is SSB. My bad. Okay, SSB. Okay, single sideband. So what are the benefits of having single sideband? Just now we talked about double sideband where we suppress the carrier. Here we suppress the carrier plus one sideband. So the benefit is the spectrum space occupies only 1/2 of that of AM and of DSB signal. So SSB compared to DSB, it saves more spectrum space compared to these both modulation. And then all the power previously devoted to the carrier and the other sidebands can now be channeled into the single sideband, producing a stronger signal that will be better for long distance transmission. And then because SSB signals occupy a narrower bandwidth, the amount of noise is also reduced. As I told you before, when we increase bandwidth, we are also increasing noise. When we reduce bandwidth, we are reducing noise. Okay. And there is less selective fading of an SSB over long distances compared to a standard AM, whereby we have carrier, we have SSB, we have harmonics. When it reaches the receiver, some of the signals have different phases, meaning to say they arrive at the receiver at different times, and sometimes because of that, they get lost. When they can't arrive in time and the window for receiving is closed, that signal is lost. So that is what is called selective fading due to the different phases. Because how does the different phases occur? Due to the loss in the air, the medium that we transmit our waves or signals, sometimes it causes phase delays. Okay, so that is selective fading. Okay, this is also SSB. So in SSB, when no information or modulating, sorry, I forgot to conclude just now. So there is less selective fading of an SSB because you are only transmitting one, so you are only expecting one. So the window for the receiver to open is just expecting one guy. And if that guy arrives, I can close. If the guy is not arriving, I keep it open. So it's pretty simple in a sense that you know what you're expecting compared to like a standard AM signal. Okay. Okay, 3 more minutes, bear with me. I think 2 more slides. Yep. Okay, so this is a single sideband suppressed carrier. Same topic. We are in the same topic. So in SSB, when no information or modulating signal is present, therefore no signal is transmitted. So if you are not speaking or you are not giving information, meaning to say you are not giving a modulating signal to the carrier, because there's no carrier in the first place, the transmission is 0. You are not transmitting anything. Therefore, you are saving energy. In a standard AM transmitter, the carrier is still transmitted even though it may not be modulated. So in a standard AM transmitter, the receiver has to receive the carrier even though there's no information. Now, that's a lot of wastage of energy because it's constantly on. It's constantly receiving even though you're not transmitting any information. It's just the carrier. So in SSB, the sidebands are generated only if there is modulation. So only when there is information, you would transmit something, okay? So here, the dashed line indicates that these guys are suppressed or eliminated by the circuit, and you are only focusing your signal over here. This is your single sideband signal. And for the time domain, you will only have one sine wave if you are transmitting sine wave. And it's not a bunch of like complex AM waveform that we saw just now. It's just a single frequency. And that's great. Unless it's not a single frequency. It's a range. It can be a range. Okay, but it's going to be simpler. Okay, so I'm gonna stop here because I think everyone is already tepu. What do you call tepu in English? I don't know. Okay, so I hope everyone understood what we talked about so far. Please revise. I will upload this on Putra Blast later. I will record the videos and will let you know when it is available. Otherwise, have a great rest of the day. If you have any questions, you can ask me now or you can leave class. Thank you, everyone.